Hello, my curious friend. I am so glad you set aside this time for us here on Deepfield Channel. Tonight we're going to lean into the strangest and most precise laws that science has ever written down, the ones that govern how reality behaves in its thinnest layers, where the world stops working the way our senses insist it should, and starts working in a way that no human language can fully describe without losing something essential along the way. I will do my very best not to make this topic so fascinating that it steals your sleep, but I will tell you right now that it will be a challenge. Before we begin, I would love to hear in the comments which corner of the world you are listening from tonight, and if you're feeling too tired to type much, just leave a simple hello. It might seem like a small thing, but that tiny gesture tells YouTube that our little space here is welcoming and helps us bring more tired minds into the fold to unwind with us. If you enjoy our scientific journeys together, please leave a like and subscribe. And to those of you who are already part of our community, thank you from the bottom of my heart. If you would like to feel even closer to what we do here, consider becoming a channel member. Members get early access to videos before everyone else. The link is in the description. Now, wherever you are, find a position that feels truly comfortable. Take one deep breath. If sleep arrives, welcome it in. Let us begin. There is a layer of the world you have never seen with your own eyes. You will never see it directly, strictly speaking, because the instruments built into your senses simply do not reach that far down. It sits below anything any eye could ever detect, below what any optical microscope ever built can reveal on its own, below what a single strand of hair could represent as a scale, and still far below even that. It is the layer of atoms and the particles that compose them, the substrate from which everything you touch, see, breathe, and feel is made. And what science has discovered about how that layer operates over the course of the 20th century was, to use the most accurate word available, unsettling. Not unsettling in the sense of threatening, but unsettling in the sense that it shakes the very foundations of what we thought we knew about what it means to exist, about what it means for something to be in a place, about what it means for two things to be separate, about what the act of observation does to the thing being observed. The physicists who built quantum mechanics in the first decades of the 20th century were, many of them, well aware that they were stepping into territory that language had never prepared anyone to describe. Werner Heisenberg, when he introduced his uncertainty principle in 1927, wrote in the years that followed about how difficult it was to communicate what the equations implied, because any analogy drawn from everyday objects would inevitably break down at some point. Niels Bohr, perhaps the most influential among the founders of the theory, used to say that anyone who was not shocked by quantum mechanics upon first encountering it simply had not understood it. That was not a warning about mathematical difficulty. It was an observation about what happens to a person's entire picture of the world when they take the implication seriously. Einstein, who made an essential contribution to the early development of this theory by explaining the photoelectric effect using the idea of light quanta, the photons, and who received the Nobel Prize for that work in 1921, spent the final decades of his life trying to prove that quantum mechanics was incomplete. Not out of pride, not out of stubbornness toward a younger generation that had surpassed his results, but because what the theory claimed about the nature of reality seemed so absurd that the most reasonable alternative appeared to be that the theory was missing something, some hidden variable, some deeper description that would restore determinism and locality. Decades of experiments later, it became clear that the theory was not missing anything at all. It was the world that had stopped behaving the way our senses expected. Einstein was wrong about this particular point, which is remarkable given that he was right about almost everything else. The first fact of tonight begins with something that seems impossible, and yet science confirms it with a regularity that leaves no room for reasonable doubt. Subatomic particles do not possess definite properties before they are measured. This is not a looseness of language. It is not a poetic way of saying we simply do not know what those properties are. It is what the theory predicts and what experiments confirm over and over again with results that no alternative theory based on pre-existing properties, can reproduce. An electron, before any interaction with the detection instrument, is not in one place. It does not have a definite speed. It does not spin in a specific direction called spin. It exists in superposition, an overlapping of all possible states that its equations allow, each one carrying an associated probability amplitude. The equation that describes this superposition, the Schrödinger wave equation, was formulated in 1926 and stands as one of the most thoroughly confirmed equations in all of physics. It describes how the superposition of states for a particle evolves over time with a precision that no experiment has ever violated. And what it says about the nature of superposition is not comforting to intuitive thinking. The undefined state is not a product of our ignorance. It is not that the electron is in some place we simply do not know, like a coin that fell behind the couch and is heads or tails regardless of whether anyone looks. The truth is that a definite location genuinely does not exist before the measurement takes place. Superposition is the real state. The definite state only emerges through measurement. Before that moment, there are only probabilities of finding the electron in different states if a measurement is performed. The coin, before anyone looks, is neither heads nor tails. It is in a superposition of heads and tails simultaneously, with amplitudes that determine the probability of each outcome, and when we find it, we collapse that superposition into a single result that the world records as final. The strangeness of superposition became famous throughout science and far beyond it because of a thought experiment that Erwin Schrödinger created in 1935 not to celebrate quantum mechanics, but to mock what he considered an absurd implication of the Copenhagen interpretation. Place a cat inside a sealed box. Inside the box there is a mechanism connected to a single radioactive atom. If the atom decays, a detector triggers a hammer that breaks a vial of poison, killing the cat. If the atom does not decay, the cat survives. Quantum mechanics says that the atom, before being measured, is in a superposition of decayed and not decayed. According to the logic of the Copenhagen interpretation, that superposition propagates to the mechanism, to the hammer, to the vial, and eventually to the cat. Until the box is opened and a measurement is made, the cat is simultaneously alive and dead. Schrödinger believed this conclusion demonstrated the absurdity of the theory, but decades of experiments have confirmed that superposition is real in increasingly larger systems, and the problem with the cat is not that the theory is wrong. It is that decoherence, which we will explore later tonight, guarantees that a macroscopic cat never remains in superposition for any measurable length of time. The superposition dissipates into the environment almost instantly on human timescales. Schrödinger's cat is never actually in superposition when you open the box, not because quantum mechanics is wrong, but because the cat interacted with so many particles in the environment inside the box that decoherence collapses any superposition on timescales far shorter than any human act of observation. The Stern-Gerlach experiment. Performed by Otto Stern and Walter Gerlach in Frankfurt in 1922, demonstrated the reality of superposition directly even before the full mathematical framework of quantum mechanics had been developed. They sent silver atoms through a non-uniform magnetic field and observed that the atoms split into two distinct beams on the detection screen. The classical explanation would have been that the electrons in the atoms, spinning like tiny charged tops, would have magnetic moments distributed continuously in all directions, and the field should scatter them into a continuous distribution on the screen. What was observed instead were two discrete spots, suggesting that electron spin can only take two possible values up or down. And even more revealingly, if you run the experiment with the field pointing in one direction, you get two groups. If you then take one of those groups and pass it through a field oriented in a perpendicular direction, you get two groups again. And if you then take one of those and pass it back through a field in the original direction, you get two groups once more, as if the measurement in the second direction had erased the information from the first. Spin did not have a value sitting there before it was measured. The measurement created the value, and it did so in a way that erased whatever had been created by the previous measurement. Superposition is real. Measurement collapses it, and there is no way to measure without collapsing. That alone would be enough for a night of deep reflection. But superposition has a direct consequence that makes it even harder to fit into any intuitive picture of how the world works, and it leads us to the second fact of tonight. If an electron can exist in multiple states at the same time, what prevents it from passing through two places at once? The answer, verified exhaustively in laboratories around the world, is nothing. Imagine a thin barrier with two parallel slits cut into it. Now imagine firing electrons toward that barrier, one single electron at a time, with a screen on the other side to record where each one lands. Classically, each electron should go through one slit or the other, and over time you would expect to see two bands on the screen directly behind each opening. What you find instead is an interference pattern, alternating lines of high and low electron concentration arriving at the screen. That pattern can only be produced by waves passing through both slits simultaneously and interfering with themselves, reinforcing where they are in phase and cancelling where they are out of phase. The electron went through both slits at the same time. It interfered with itself like a wave on the surface of water, encountering a barrier with two openings and creating interference patterns on the other side. Only after interfering did it reappear as a particle at one specific point on the screen. Each individual electron contributes a single dot on the screen, as if it were a discrete particle. But over many detections, the dots accumulate into a pattern that only waves can produce. Wave-particle duality is not the idea that light and matter are sometimes one thing and sometimes another depending on convenience. It is that they are both things at the same time, in ways that only become distinguishable depending on how the question is asked. Before the question is asked, the particle is something that the available vocabulary cannot name adequately, because that vocabulary was built from experience with large objects, and large objects do not behave this way. The double-slit experiment has one additional detail that pushes the absurdity one step further beyond what has already been described, and it points directly to where our conversation needs to go next tonight. If you place a detector at one of the slits to find out which one the electron passed through, the interference pattern disappears. Immediately. Completely. The electron goes to one side or the other, and the bands that accumulate on the screen correspond to what you would expect from classical particles passing through one slit at a time. The mere presence of information about which slit the electron crossed, even before any conscious being has looked at that information, even if the detector records the data and it is erased before anyone reads it, collapses the superposition. It is not consciousness that causes this. It is the availability of information in the physical world, and this result, replicated in experimental variations that exclude every possible alternative explanation creative physicists could imagine, changes what observation means. To observe is not to passively receive what is already there. At the quantum level, to observe is to participate in the creation of what comes to be there. The question left hanging after the double-slit experiment is one of the deepest and most resistant to answer in all of modern physics. What exactly happens when we measure? What is this collapse of the wave function? Who or what performs it? And where is the boundary between the domain where superposition exists and the domain where everything has definite positions and velocities? These questions are not philosophical in the decorative sense, not questions without consequences for real experiments. Different interpretations of quantum mechanics give radically different answers to them, and although all of them reproduce the same predictions for current experiments, they imply worldviews that are mutually incompatible in ways that have consequences for how we think about causality, locality, and the nature of time. We will return to those interpretations later. But first, there is a fact that must be presented because it is perhaps the most disorienting fact in all of quantum mechanics, not because of any complexity in the mechanism, but because of the simplicity of the result and the radical nature of what it implies. Imagine two electrons that interact briefly in a laboratory and are then separated and sent in opposite directions, one to a detector in Rio de Janeiro and the other to a detector in Tokyo. After the interaction, they are no longer two independent systems. They form a single system, described by a single wave function that contains both of them and that cannot be factored into the product of two individual wave functions. This state is called an entangled state. When you measure the spin of the electron in Rio de Janeiro, the result is random. It can be up or down, but whatever the result turns out to be, the electron in Tokyo is immediately found in the opposite state, regardless of the distance between them, regardless of any signal that could travel from one to the other, regardless of how long it takes to compare the two results. The correlation is instantaneous in every reference frame, and it is stronger than any correlation that could exist between systems that shared information in the past and then separated. Einstein called this spooky action at a distance in a paper from 1935 that he wrote with Boris Podolsky and Nathan Rosen, a work whose author's initials form the acronym EPR. The argument in the paper was precise and elegant. If measuring one electron instantly determines the state of another far away, then either information is propagating instantaneously between them, which would violate relativity, or the state of each particle was already determined before the measurement by variables that quantum mechanics does not describe, hidden variables carrying the instruction for which result each particle will produce. The second option seemed more reasonable to Einstein. Quantum mechanics would be incomplete, missing a description of something that was already there. The EPR paper became one of the most influential philosophical contributions to 20th century physics, not because it was right, but because it formulated the problem with a clarity that made it testable decades later. In 1964, the Irish physicist John Bell, working at CERN, derived a mathematical inequality that separated the predictions of standard quantum mechanics from the predictions of any theory using local hidden variables. The inequality specified a limit on the correlation between measurements on separated particles that no local realist theory could violate, and it showed that quantum mechanics predicted that this limit would be violated. Bell was not pessimistic about the possibility of hidden variables. He had no preference for the outcome. It was an experiment that could, in principle, settle what had been a philosophical debate for decades. Experiments to test Bell's inequality began in the 70s, with results that became progressively more rigorous. Alain Aspect and his collaborators in France carried out a set of experiments in the 80s that closed most of the obvious loopholes in earlier versions, and showed that the correlations between entangled particles violated Bell's inequality in a way consistent with the predictions of quantum mechanics. In 2015, 3 independent groups in different countries performed experiments that closed the 2 main remaining experimental loopholes simultaneously, in what became known as loophole-free Bell test experiments. The results violated Bell's inequality with a margin that excludes local hidden variables with a statistical confidence equivalent to being certain that you're not dreaming right now. The universe does not have local hidden variables. Entanglement is real. The correlations between particles that interacted in the past are stronger than any classical mechanism can produce, and there is no way to explain them with any model in which each particle carries a pre-existing instruction about which result it will produce. The only explanation that works is that the 2 particles continue to be part of a single quantum system, and that the state of this system is not described by independent properties of the 2 particles, but by properties of the pair as a whole, properties that cannot be broken down into individual ones. This does not allow information to be transmitted faster than light. The result of any individual measurement is genuinely random, and the correlation only reveals itself when the 2 results are compared through classical means that obey relativity. The experiment does not violate causality, but it does violate locality, the idea that what happens here can only be influenced by what is here or by what travelled here in the past. At the level of entangled particles, what happens here is instantaneously correlated with what happens there, and that correlation has no local explanation. The physicist David Bohm, who dedicated decades to trying to formulate a version of quantum mechanics with hidden variables that would work, eventually arrived at an interpretation that took entanglement seriously as a fundamental property of the entire universe. In his model, the field that guides the particles carries information about the complete configuration of the universe in a non-local way. Everything is connected to everything else through this universal wave field, and what we call separate objects are excitations of an indivisible whole that Bohm called the implicate order. The deeper reality from which the world we perceive, the explicate order, emerges as a projection. Bohm used the metaphor of a hologram. Every fragment of a hologram contains information about the entire image, not in a vague way, but in a way that the whole image can be reconstructed from any fragment, though with less resolution. The universe would work the same way. Every part contains information about the whole, and the separation between things is more apparent than fundamental. Bohm's interpretation never became dominant because it has difficulties reconciling with special relativity, which requires that equations take the same form in all reference frames. But it is mathematically consistent. It reproduces all the predictions of standard quantum mechanics, and it was taken seriously by physicists like Bell, who said it was proof that quantum mechanics could be interpreted in a realistic and deterministic way, even if at the cost of non-locality. Non-locality, as the entanglement experiments have made clear, is not a price we choose to pay in order to have determinism. It is a feature of the universe that the equations reveal regardless of which interpretation we adopt. And if entanglement connects what seems separate, what comes next challenges something even more basic: the very possibility of knowing the world with arbitrary precision, even from a single point in space. In 1927, working in Copenhagen, Heisenberg was thinking about what would happen in practice if we tried to measure the position of an electron using light. To locate something with precision, you need short wavelengths. Short wavelengths correspond to high frequencies, which in turn correspond to photons carrying more energy. A high-energy photon that strikes an electron to determine where it is will inevitably transfer some of its momentum to the electron, altering the electron's momentum in proportion to the precision with which we tried to measure its position. Using low-energy photons to avoid disturbing the electron means using long wavelengths, which limits the precision with which we can locate the position. Precision in position and precision in momentum trade off against each other. Gaining one cost the other. Heisenberg formalized this trade-off in a mathematical relationship. The product of the uncertainties in position and momentum is always greater than or equal to Planck's constant divided by 4 pi. But the more careful derivation, carried out by the mathematicians who developed the algebra of quantum operators in the years that followed, revealed something deeper than the argument about disturbance by measurement. The uncertainty is not caused by the disturbance of the instrument. It is an intrinsic property of matter waves, a wave function that is perfectly localized at a single point in space, an infinitely narrow peak, is mathematically equivalent to the superposition of infinitely many frequencies, and therefore has a completely undefined momentum. A wave function with a perfectly defined frequency, a regular oscillation extending across all of space, has a completely undefined position because it is everywhere at once. Localization and frequency are complementary pairs in the mathematics of waves, and since momentum is proportional to frequency and position, is the spatial analogue of localization, the uncertainty between position and momentum is mathematically inevitable, independent of any instrument or disturbance. The universe has a fundamental imprecision woven into its very constitution, not as a flaw, not as a limitation of our tools, as a property. This conclusion was difficult to accept in 1927, and it remains difficult to accept today. The physics that preceded Heisenberg was deterministic in the strongest sense. Knowing the state of the universe at a given instant with arbitrary precision would, in principle, make it possible to calculate the state at any future instant. Pierre-Simon Laplace, the French mathematician of the 18th century, formulated this ideal with a clarity that has endured in history. If there existed a being with sufficient intelligence to know the positions and velocities of every particle in the universe at a given moment, that being could calculate everything that would happen in the future and everything that had happened in the past. Classical determinism was total. Chance was merely a word for our ignorance, an epistemological category, not a property of reality. Heisenberg destroyed that ideal definitively. The uncertainty principle is not a limitation on what we can know in a practical sense. It is not that the instruments are insufficient or that the calculation is too difficult. It is that the variables Laplace assumed existed with precise values, the simultaneous position and momentum of every particle, do not exist in nature. Laplace's demon could not know what it would need to know to make its predictions, not because it would be difficult, but because what it would need to know is not there to be known. Chance is an ontological property of the universe, not a category of ignorance. The universe is fundamentally indeterministic. The future is not completely determined by the present. This conclusion is not universally accepted among physicists. Bohm's interpretation, with its hidden variables, restores determinism at the cost of non-locality. And the debate over whether quantum randomness is genuine or apparent is part of the interpretation problem we will explore later. But the majority of physicists work from the position that randomness in quantum mechanics is real, and that Heisenberg's uncertainty describes a limit of reality itself, not a limit of our ability to measure it. Uncertainty is not merely a limitation on what we can know. It is also, paradoxically, the source of something that makes the universe habitable, that makes stars possible, and that made life possible before anything else. To understand how a limitation on knowledge becomes a source of energy, we need to consider what happens when a particle encounters a barrier that, classically, it should not be able to cross. In classical physics, the situation is straightforward. If a ball does not have enough kinetic energy to climb a hill, it does not climb. It hits the slope, stops, and rolls back. The barrier is insurmountable. In quantum physics, because the position of a particle is inherently uncertain, because it exists as a probability distribution rather than a definite point, there is always a probability, small but calculable and not zero, that the particle will appear on the other side of the barrier without having classically passed through it. It did not climb over the barrier. It did not go around the barrier. It went through the barrier beneath it, in terms of the topology of the energy landscape described by the equations. The technical term for this is quantum tunneling, and it is as real and as mathematically necessary as any other effect in quantum mechanics. The Sun has a core temperature of approximately 15 million degrees Celsius. That is hot by any human standard, but it is not hot enough for the protons in the solar core to have sufficient kinetic energy to overcome the electromagnetic repulsion between two positive charges and get close enough for the strong nuclear force, which only operates at distances on the order of a femtometer, to take over and allow fusion. According to classical physics calculations, protons should almost never fuse under the conditions in the solar core. The classically predicted fusion rate is orders of magnitude lower than the rate we observe. The Sun, according to classical physics, should shine far less brightly than it does, or perhaps not shine at all under the conditions it has. Quantum tunneling resolves this problem precisely. Because the position of each proton is distributed in probability, there is always a non-zero tail of that distribution that extends beyond the electrostatic potential barrier. Protons tunnel, with a minuscule probability in each individual encounter, but the Sun has such an enormous number of protons and such a high collision rate that this improbable event happens roughly 845 sextillion times per second, a number that written out in full would occupy an entire sentence on its own. All the energy that warmed any afternoon you have ever lived, that fed any plant that has ever existed on this planet, that evaporated oceans and brought them back as rain, came from this mechanism. The star that sustains us is, in its deepest essence, a quantum tunneling reactor. And tunneling is not exclusive to the Sun, nor to any particular star. It happens in the interior of each of the hundreds of billions of stars in the Milky Way, and in each of the hundreds of billions of galaxies within the observable universe. The mechanism that seems like an anomaly is the mechanism that illuminates the entire cosmos. Every point of light you would see looking up at the sky on a dark, clear night is there because particles pass through barriers they classically could not cross. Quantum tunneling also operates at the scale of the world you use every day, in a way that very few people who use those devices are aware of. The modern transistor, the component at the foundation of every electronic circuit since the 50s, has in its most recent versions dimensions of just a few nanometers, comparable to the size of certain molecules. At that scale, electrons that should be blocked by insulating oxide layers between the terminals of the transistor cross those layers through tunneling at a rate that engineers must calculate and control with precision for the device to function as intended. Tunneling is not an unwanted residual effect. In certain types of semiconductor memory, it is the intentional mechanism by which information is written and erased. The technology most present in contemporary daily life operates through quantum tunneling. Now, if tunneling depends on the uncertainty of particle position, that uncertainty in turn depends on something even more fundamental about the nature of how energy exists in the universe. And this is where we arrive at the fifth fact of tonight, which begins not with a particle passing through a barrier, but with a German physicist trying to solve what appeared to be a technical engineering problem in industrial manufacturing at the end of the 19th century. Max Planck was working in Berlin at the end of the 1800s for a company that manufactured lamp filaments, and he needed to understand more precisely how heated objects emit electromagnetic radiation as a function of temperature. The classical physics of the period, applying thermodynamics and Maxwell's electromagnetism to the problem, predicted that a heated body should emit more and more energy at increasingly shorter wavelengths. The shorter the wavelength, the more vibrational modes of the electromagnetic field would be available at that frequency, and each mode should receive the same average energy per degree of temperature. The result was that the radiated energy should grow without limit at high frequencies, diverging toward infinity. What became known as the ultraviolet catastrophe was not a marginal prediction or a controversial interpretation. It was the direct result of the most rigorous physics available at the time, and it was flagrantly wrong. Real heated bodies clearly did not emit infinite energy. Planck solved the problem in 1899 by introducing the hypothesis that energy cannot be exchanged in any continuous amount, but only in whole number multiples of a minimum unit whose size is proportional to the frequency of the radiation. He called this minimum unit a quantum of energy. The constant of proportionality between frequency and the minimum energy quantum is what we now call Planck's constant, represented by the letter h, and its value is approximately 6.6 times 10 to the negative 34th joule seconds, an extraordinarily small number, which explains why quantum effects are not noticeable at everyday scales. Planck did not initially believe that quantization was real. He thought it was a convenient mathematical trick, a formal device without physical correspondence, and that someone would eventually explain the black body radiation data in a more orthodox way. It took years, and the intervention of Einstein with the theory of the photoelectric effect in 1905, for it to become clear that quantization is real. Energy truly comes in discrete packets, the quanta, and not in any continuous amount. There is nothing between one energy level and the next. The universe at its smallest scales is granular, and Planck's constant is the scale of that granularity. The quantization of energy has a consequence that seems to violate what intuition says about what emptiness means, about what nothingness is. And that is the sixth fact of tonight, which begins with a question that seems simple. What is the vacuum? The classical answer is immediate. The vacuum is space with no particles, no radiation, no matter or energy whatsoever. It is literally nothing, the absence of everything. If you removed all matter and all radiation from a region of space, what would remain would be the vacuum, and the vacuum would be zero. Zero energy, zero field, zero of everything. The quantum answer is radically different. Heisenberg's uncertainty principle, applied not to position and momentum but to the pair energy and time, implies that the energy of a system on a very short time scale is inherently uncertain. The shorter the time interval you consider, the greater the allowed uncertainty in energy, and the quantization of energy, combined with that uncertainty, implies that even the lowest possible energy state of any quantum field is not exactly zero. There are always fluctuations. The field has what physicists call zero-point energy, even in its ground state, and these vacuum energy fluctuations have measurable physical consequences. Particles and antiparticles spontaneously appear in pairs in empty space, exist for a time interval that the energy-time uncertainty allows, and then annihilate each other, returning the energy to the field. The vacuum seethes with activity that cannot be directly observed because the particles vanish before any detector can register them, but it leaves physical marks on the world that the theory predicts and experiments confirm. Quantum tunneling, which we explored as the mechanism that powers the sun, also operates in biological processes that perhaps no one would have ever thought could be quantum. DNA repair, the process by which cells detect and correct errors in the copying of genetic material, involves the transfer of protons between DNA bases. The rate and precision with which these transfers occur at physiological temperature are compatible with quantum tunneling of protons through potential barriers they would not classically cross. This is an area of active research, and the evidence is not yet definitive, but the possibility that the integrity of the genome, the preservation of genetic information across generations, depends partly on quantum tunneling is serious enough to have produced sustained investigation. There is also the phenomenon of electrons in biological molecules such as enzymes, which catalyze chemical reactions by accelerating them by factors ranging from 1 million to 1 trillion compared to the uncatalyzed reaction. Part of the efficiency of enzymes has been attributed to quantum tunneling of protons and electrons in various catalyzed reactions, and there is experimental evidence published by groups such as that of chemist Judith Kleinman at Berkeley, showing that some enzymes exploit quantum tunneling to achieve rates that would not be attainable through classical mechanisms. Biology, from this perspective, does not merely tolerate quantum effects as background noise that decoherence quickly dampens. In some cases, it appears to have incorporated them as functional mechanisms over billions of years of evolution. The boundary between quantum physics and biology is one of the most active and most contested frontiers in contemporary science. Proponents of quantum biology argue that life has found ways to exploit quantum mechanisms that artificial systems cannot yet imitate. Skeptics argue that biological environments are too warm and too wet for quantum coherence to survive on timescales and length scales relevant to biological function. The debate, like so many at the edges of knowledge, does not yet have a definitive answer. But the very existence of the debate is itself a datum. The boundary between the quantum and the biological is more porous than anyone imagined. The most direct and best measured effect of the virtual particles of the quantum vacuum was predicted by the Dutch physicist Hendrik Casimir in 1948, starting from a relatively simple idea that produces a surprising result. If you place two parallel neutral metal plates very close to each other in a perfect vacuum, they should remain motionless. There is no charge between them, no currents, no classical fields that would make them interact. But the virtual particles that emerge from the vacuum, though they cannot be detected individually, have wavelengths that must fit between the plates. Within the space between the plates, only the oscillation modes of the quantum field whose wavelengths fit between the surfaces are allowed. Outside the plates, all wavelengths are possible. This creates a pressure difference. The vacuum outside the plates has more available modes and therefore more activity than the vacuum between them. That pressure difference pushes the plates toward each other. The resulting force, called the Casimir force, was first measured experimentally in 1997 by the physicist Stephen Lamoureux with a precision of 5%. Subsequent experiments measured the Casimir force between surfaces of different geometries with increasing precision, confirming the theoretical predictions in ever more rigorous ways. Nothingness exerts force. The vacuum has pressure. Absolutely empty space pushes metal surfaces toward each other in a way that is measurable and calculable. No physics student in the 19th century could have predicted this, because no prior physics had ever conceived of a vacuum that seethed with activity. This creates a problem that physics has not yet resolved satisfactorily, and it represents the largest disagreement between theory and observation in the entire history of science. If the quantum vacuum has energy, that energy must contribute to the total energy of the universe, and therefore to the curvature of space-time described by general relativity. When physicists calculate how much this energy should be using quantum mechanics without any ad hoc correction, the result is roughly 120 orders of magnitude larger than the cosmological constant that astronomical observations measure. 100 times 10 raised to the 90th power. This is the so-called cosmological constant problem, and it is the largest numerical disagreement between theory and observation that exists anywhere in physics. The two best confirmed theories in science, quantum mechanics and general relativity, when they meet on the question of vacuum energy, produce a conflict that no one knows how to resolve. But returning to the vacuum and what it teaches us, there is another phenomenon that the quantum vacuum allows, and that has consequences for the structure of the universe on a scale far larger than the Casimir effect. The energy fluctuations of the vacuum are not homogeneous in time. They are random, unpredictable, distributed in ways that quantum mechanics describes statistically but never determines exactly for each individual case. And that means that in the very beginning of the universe, when scales were so small that all the physics we know was compressed into a volume with no equivalent in any human experience, quantum vacuum fluctuations produced density variations that the expanding universe amplified into structure. Facts 7, 8 and 9 of tonight about decoherence, interpretations and connections with the cosmos will explore that territory more carefully. But what is clear here is that the vacuum is not merely the absence of matter. It is the substrate from which matter emerges and from which the structure of the visible universe was, in part, generated. This substrate has properties that classical physics has no vocabulary to describe. It has energy, it has fluctuations, it has pressure, and under certain conditions, it has the ability to create real particles from nothing, in processes that general relativity permits in the presence of sufficiently intense gravitational fields. Stephen Hawking demonstrated in 1974 that black holes, because of the extreme curvature of spacetime near the event horizon, should emit thermal radiation created by pairs of particles that emerge from the vacuum near the horizon. One of the particles falls into the black hole while the other escapes to infinity. The black hole loses energy in this process and eventually, over a very long time, evaporates. Hawking radiation has not yet been detected observationally, because astronomical black holes emit at temperatures so close to absolute zero that any signal would be obscured by the cosmic microwave background. But the mechanism has been calculated in different ways by independent physicists and is considered robust. It is one of the few predictions that connects quantum mechanics and general relativity in a mathematically consistent way, and its calculation involves both the equations of quantum field theory and the geometry of curved space-time. Confirming Hawking radiation observationally is one of the long-term goals of experimental astrophysics. The vacuum, then, is not neutral. It is not passive. It is dynamic, energetic, and plays an active role in the physics of the universe at scales ranging from the laboratory to the cosmological. The nothingness we imagine to be the absence of everything is, in quantum physics, one of the richest and most consequential objects in the entire theoretical edifice. And it is in this richness of the vacuum and in the fluctuations it produces that the root lies of something that emerged so early in the universe that it predates any structure we observe today, something that determined the appearance of the entire cosmos before the first atom ever formed. Cosmic inflation, the period of accelerated expansion that most cosmological models place in the earliest instance of the universe, probably within the first 10 to the negative 36 seconds after the Big Bang, amplified quantum vacuum fluctuations from subatomic scales to cosmological scales. Before inflation, the fluctuations existed only in regions causally connected to each other, too small to produce structure on large scales. During inflation, space expanded so rapidly that regions that had been in causal contact were separated beyond the cosmological horizon, freezing the quantum fluctuations into patterns that the subsequent universe inherited. The signature of those primordial fluctuations is imprinted in the temperature variations of the cosmic microwave background, with a precision of 1 part in 100,000, and the spectrum of those variations agrees with the predictions of quantum inflation with a precision that no alternative model can match. What this means in the most direct terms is this: every galaxy that exists, every nebula, every cluster, every filament of the cosmic web had its seed in a quantum fluctuation of the vacuum that was amplified by inflation and then by gravity over billions of years. The stars that exist because of quantum fluctuations. The planets that orbit those stars exist because of quantum fluctuations, and the organisms that on some of those planets evolved and created language and mathematics and physics, and came to discover that their existence originates in quantum fluctuations also exist because of those fluctuations. There is something circularly strange about this conclusion. Quantum mechanics is the theory that explains the existence of the conditions that made the development of quantum mechanics itself possible. In the first instance after the Big Bang, in an epoch when the entire universe had dimensions so small that any geographic analogy would be grotesque, the temperature and density were so extreme that the distinction between matter and radiation was fluid, and quantum vacuum fluctuations were not irrelevant background noise. They were density variations on a scale that, over the subsequent expansion of the universe across billions of years, were amplified by gravity into ever larger structures. The slightly denser regions attracted more matter, became even denser, attracted even more matter, in a gravitational feedback process that over nearly 14 billion years created the cosmic web that telescopes observe today. Immense filaments of galaxies connecting dense nodes of clusters, separated by voids of dimensions that exceed the capacity of any direct visualization. The asymmetry of the universe, the fact that it has structure instead of being a homogeneous gas expanding uniformly, is of quantum origin. The seeds of galaxies, of stars, of planets, and of all the organisms that on any of them evolved are quantum fluctuations of the vacuum of the primordial universe, amplified by time and gravity to produce the complex and heterogeneous cosmos we inhabit. This statement is one of the most verified in modern cosmology. The temperature variations in the cosmic microwave background, the remnant radiation of the Big Bang that permeates the entire universe, have a fluctuation spectrum that agrees with extraordinary precision with what would be expected if the primordial seeds were quantum fluctuations amplified by the expansion of the universe. The map of those variations, measured by satellites such as WMAP and Planck, is a portrait of the universe at roughly 378,000 years of age, and the patterns it shows, the scales at which fluctuations are larger or smaller, are the signature of quantum processes that took place in the very first instance after the Big Bang. We arrive at the 9th fact of tonight, which answers a question that anyone who has encountered the previous facts eventually formulates. If all of this is real, if particles exist in superposition, if the vacuum seethes, if entanglement connects what seems separate, why does the world around us look so solid, so localized, so clear in its distinctions? Why do you not experience superposition? Why is the chair beside you not simultaneously in two places? The answer was developed mathematically primarily from the work of the German physicist Heinz-Dieter Zeh in the 70s and deepened by Wojciech Zurek in the decades that followed. The concept is called quantum decoherence, and understanding it changes how one imagines the relationship between the quantum world and the classical world. A quantum system in superposition, like an electron that has not yet been measured, can exist in that state as long as it remains sufficiently isolated from the surrounding environment. The problem is that total isolation is impossible for any object of macroscopic size. An object of visible size is constantly being struck by photons of light, by air molecules, by phonons in the structure of materials in contact with it, by particles of every kind that make up the environment. Each of these interactions is, in mathematical terms, a kind of partial measurement. The electron or photon or air molecule that interacts with the system begins to carry information about the state of that system. The quantum system and the environment become entangled, and when a quantum system is entangled with a sufficiently large number of environmental particles, the interference terms that would produce visible quantum effects, the fringes of the double-slit experiment for example, are diluted into correlations with the environment that become practically impossible to recover. Superposition does not disappear in an absolute sense. In rigorous mathematical terms, the wave function that includes both the system and the environment continues evolving according to the Schrödinger equation without collapsing. What happens is that the information about the superposition spreads into so many degrees of freedom of the environment, into so many photons, into so many air molecules, into so many thermal degrees of freedom, that it becomes practically irrecoverable by any local observation. An observer who has access only to the system, without access to the complete state of the environment, sees a system that behaves as if it had collapsed into a definite classical state. It is as if the secret of the superposition were whispered to so many listeners that tracking any one of them individually becomes impossible in practice, even though the information continues to exist in a scattered form throughout the environment. The speed of decoherence increases with the size of the system and with the strength of its interaction with the environment. For an isolated electron, decoherence can take fractions of a second or longer, enough time for interference experiments. For a moderate molecule of a few dozen atoms in air, it happens in femtoseconds, millionths of billionths of a second. For a grain of dust of visible size in a time no current instrument can measure. For a chair, for a human being, for any macroscopic object in any normal environment, decoherence is so instantaneous on any human timescale that the difference between it and a genuine collapse of the wave function is mathematically subtle but experimentally indistinguishable. The classical world is not above the quantum laws. It is subject to them, but under conditions where decoherence occurs on timescales so short that no instrument could capture the superposition before it dissipated into the environment. The solidity that the senses perceive is real. It is the emergent result of quantum systems interacting with quantum environments in a way that makes interference effects inaccessible in practice. Quantum strangeness is not hidden behind the visible world like a concealed stage. It is everywhere, but in macroscopic systems it does not have time to produce observable effects before it spreads into the degrees of freedom of the environment. Decoherence resolves many of the tensions between the quantum and the classical in an elegant way, but it does not solve the measurement problem completely. It explains why we do not see macroscopic objects in superposition. It does not explain why, of all the possible outcomes of a measurement, only one manifests for any particular observer. It does not explain where exactly the boundary lies between the system and the environment that is measuring it. And this is where we arrive at the 10th and final fact of tonight, which is the most disorienting of all, not because of what it reveals, but because of what it fails to reveal. Quantum mechanics has a mathematical core that all physicists accept and use. The equations work. The predictions match experiments without exception across a century of increasingly rigorous tests. What does not exist is consensus about what those equations mean, about the nature of the reality they describe. This problem is called the interpretation problem of quantum mechanics, and it remains open after nearly 100 years since the theory was founded. In the Copenhagen interpretation, which for decades was the standard position taught in physics courses, there is no sense in asking what a quantum system is before it is measured. The wave function does not describe reality. It describes what we know about possible outcomes of measurements. Collapse is not a physical event that happens in the world. It is an update of information on our side. Asking where the electron was before measuring is like asking what the speed of an object was before any object existed. The question lacks a referent. Quantum theory in the Copenhagen interpretation is inherently anti-realist about the world between measurements. This satisfies many physicists who prefer to limit the theory to what can be said about experimental results, and it unsettles many others who want to know what is happening in the world independently of whether anyone is measuring. Hugh Everett, a doctoral student of John Wheeler at Princeton, proposed in 1957 a radically different interpretation, known today as the many worlds interpretation or the Everett interpretation. In it, the collapse of the wave function never happens. The Schrödinger equation governs everything always, without exception, without collapse, without distinction between quantum system and measuring apparatus. When the measuring apparatus interacts with the electron, the combined state of the electron plus the apparatus evolves into a superposition of two states. In one, the apparatus records spin up. In the other, it records spin down. The environment then becomes entangled with this system, and so on until the human observer also enters the superposition. In one branch, the observer sees spin up, in the other, spin down. Both branches continue coexisting in the universal wave function and never interact again after decoherence. Each branch is equally real. In each branch, the beings that exist have the experience of having seen a definite result. Quantum strangeness does not disappear. It multiplies into infinite parallel universes where all possible outcomes are realized in some branch. David Bohm, as we mentioned earlier, developed a deterministic hidden variable interpretation in which particles have real positions at all times, but are guided by a wave field that carries information about the complete configuration of the universe in a non-local way. The result of any measurement depends both on the initial position of the particle and on the state of the guiding field, but since we do not have access to the exact state of the field, the result appears random from our point of view. Bohm's theory reproduces all the predictions of standard quantum mechanics and is completely deterministic, but it requires genuine non-locality and encounters difficulties reconciling with special relativity in its most developed versions. There are other interpretations: stochastic mechanics, the relational interpretation of Ravelli where quantum states are relative to each observer, quantum Bayesianism which treats the wave function as a catalogue of an agent's beliefs about future experiences, and approaches based on information theory. Each of them is mathematically consistent. Each reproduces the experimental predictions, and none can be distinguished from the others by any available experiment. The 10th fact of tonight is this: the theory that describes the most fundamental level of reality with the greatest precision science has ever achieved still does not have an interpretation accepted by consensus about what it means. Physicists use the equations to build lasers and magnetic resonance machines and computers and atomic clocks of extraordinary precision, and at the same time they cannot agree whether particles have real positions when they are not being measured, whether the universe branches into parallel branches at every quantum event, or whether the wave function describes reality or merely an agent's knowledge about it. This state of affairs has no parallel in any other area of science. The theory works perfectly. No one knows for certain what it says about the nature of the world. There is a difference between knowing something and feeling the weight of what it means. You can memorize the 10 facts we explored tonight. Repeat that particles exist in superposition before being measured, that entanglement connects particles separated by any distance, that the vacuum seethes with virtual particles, that the universe has a fundamental imprecision, and all of it can remain stored information with no consequence for the way you perceive the world around you. The true strangeness begins when you try to feel that these laws are operating right now, in the atoms of the air you breathe, in the molecules of the blanket that warms you, in every electron orbiting every nucleus of every atom in your body. Let us try to bring that closer. Every atom in your body was synthesized inside a star that lived and died before the sun was formed. The carbon in every DNA molecule in your cells was forged inside massive stars through the nuclear fusion of helium, in a process called the triple alpha process, where 3 helium nuclei fuse in sequence to produce carbon-12, and which is only possible because one of the states of carbon has a resonant energy that matches the energy available in the reaction. The physicist Fred Hoyle predicted this resonance in 1953 from the argument that since carbon exists abundantly in the universe, and since life is carbon-based, physics must allow carbon to be synthesized efficiently, and therefore this resonant state must exist. It was a form of reasoning that irritated many physicists because it seemed teleological, but the resonance was discovered in the laboratory exactly where Hoyle predicted. The carbon atoms in your body arrived here by that route, forged in stars, scattered in supernova explosions, collected by the molecular cloud that became the solar system, incorporated into the planet and then to life. And every one of those atoms from then until now has obeyed the quantum laws we have described. But quantum physics is not only in the past of your atoms or at the imperceptible scale of your particles. It is operating right now in biological processes happening while you rest. Photosynthesis is the process by which plants, algae, and certain bacteria convert sunlight into stored chemical energy. At the molecular level, this involves the capture of a photon by a pigment molecule and the transfer of the resulting energy to the reaction center where the chemistry takes place. An aspect that puzzled biologists for decades is that this energy transfer is extraordinarily efficient, far more than classical physics would predict for a process of energy transfer by hopping between molecules. Experiments conducted in the early 2000s using ultra-fast laser spectroscopy techniques revealed that the energy, after being absorbed, propagates toward the reaction center by traversing multiple simultaneous paths through the protein complex, with interference patterns between the paths that increase the efficiency of arrival at the destination. The behavior was consistent with quantum coherence, with the energy existing in superposition of multiple paths before arriving at the destination through a combination of them. The debate over whether this is genuine quantum coherence or a sophisticated classical effect is still ongoing in the scientific literature, with arguments on both sides. But the possibility that life uses quantum superposition to optimize energy transport is real enough to have generated an entire field of research called quantum biology, which investigates the potential roles of tunneling, entanglement, and superposition in biological processes. The sense of smell is another biological system under quantum investigation. The classical theory of olfaction says that odorant molecules are recognized by olfactory receptors exclusively by their shape, like a key fitting into a specific lock. The geometry of the molecule determines which receptor it binds to, and therefore which odor is perceived. An alternative theory, proposed by the biologist Luca Turin, suggests that olfactory receptors are sensitive not only to the shape of molecules, but to the vibrational frequencies of the bonds within them, and that the detection mechanism involves quantum tunneling of electrons through the odorant molecule when it is coupled to the receptor. Experiments with isotope molecules, which have the same shape but different vibrational frequencies due to the mass difference between hydrogen isotopes, produced results that in some contexts are difficult to explain purely by the shape theory, but the results are contested and the question remains in active scientific debate. The most studied case of a quantum phenomenon in biology is the magnetic navigation of migratory birds. Several species of birds undertake migrations of thousands of kilometers with a navigational precision that exceeds what any purely classical internal map could explain. Experiments have demonstrated that at least part of the sensitivity to the Earth's magnetic field operates in the eye of the birds and is light-dependent. Birds blinded in the right eye lose the ability to use the magnetic field for navigation, in a way that birds blinded in the left eye do not, suggesting that the magnetic compass system is lateralized to the right eye. The proposed mechanism is that of radical pairs. When a photon is absorbed by a cryptochrome, a light-sensitive protein present in many organisms, it produces a pair of electrons with entangled spins. The subsequent evolution of the spin of this pair in the Earth's magnetic field is sensitive to the orientation of the field, and the outcome of the chemical process that these electrons activate depends on that orientation. The bird, in essence, uses the quantum entanglement of electron pairs as a compass. This mechanism was proposed by Klaus Schulten in the 70s, and has received growing experimental support since then. though the definitive demonstration that it is indeed the mechanism operating in vivo is still a matter of active research. The technology that quantum mechanics made possible over the course of the 20th century represents an enormous fraction of everything that distinguishes the contemporary world from any prior period in human history. The transistor, invented by John Bardeen, Walter Brattain, and William Shockley at Bell Labs in 1947, is the fundamental component of every electronic circuit built since then. The operating principle of the transistor depends on the quantum behavior of electrons in semiconductors, on the Pauli exclusion principle that determines how electrons distribute themselves among the energy levels of a solid, and on the tunneling properties that become dominant in the most recent versions manufactured at nanometer scales. Without quantum mechanics, there is no understanding of semiconductors, and without semiconductors, there are no transistors, and without transistors, there is no electronic device that exists today. The laser, which emerged from theoretical developments based on the quantum mechanics of stimulated emission of radiation, is present in barcode readers, fiber optic telecommunications, eye surgery, holography, high-precision metrology, and in any high-resolution screen that works with laser diode backlighting. Nuclear magnetic resonance used in clinical medicine is a completely quantum phenomenon. The spin of protons in biological tissues aligns with external magnetic fields in ways that depend on quantum mechanics, and the relaxation signals from that alignment carry information about the molecular structure of tissues that algorithms transform into diagnostic images. GPS works with atomic clocks, which are clocks whose oscillations are calibrated by the frequency of the transition between two hyperfine states of the cesium-133 atom, a frequency so precise and so stable that it allows time synchronization with nanosecond precision. Quantum computing, which is being actively developed by laboratories in several countries, and by companies like IBM, Google, and various specialized firms, uses qubits, units of quantum information that can exist in superposition of 0 and 1 simultaneously, to process information in ways that classical computers cannot reproduce efficiently. Certain categories of problems, such as factoring integers into prime factors and searching unstructured databases, can in principle be solved by quantum computers in much less time than any classical computer could manage. Other problems, such as simulating molecules for the discovery of new drugs or optimizing complex logistical systems, appear to be natural candidates for quantum advantage when the systems are sufficiently developed. The central technical challenge is keeping qubits sufficiently isolated from the environment so that decoherence does not destroy the quantum information before the computation is complete, and advances in quantum error correction and in the control of many qubit systems have been substantial in recent years. Quantum cryptography, in contrast to quantum computing, already operates in practical implementations. Quantum key distribution, based on the principle that any attempt to measure a quantum state will disturb it in a detectable way, allows cryptographic keys to be established between 2 points, with the guarantee that any interception will leave visible traces in the data. Quantum communication networks exist at test scale in several countries, and China has operated quantum entanglement experiments by satellite that established correlations between stations separated by more than 1,000 kilometers through space, using the Messier satellite launched in 2016. The most counterintuitive physics that science knows is also the foundation of the most secure communication technology that exists. What unites all these technological advances is something that rarely appears in narratives about innovation. They were not developed by engineers who needed solutions to practical problems and went looking for physics. They were developed by physicists who were trying to understand how the world works at a fundamental level, with no practical application in mind. The transistor came from the theoretical understanding of semiconductors. The laser came from the physics of stimulated emission of radiation that Einstein developed in 1917, decades before any practical application was conceived. Nuclear magnetic resonance was discovered by Isidor Rabi as a fundamental physics phenomenon in 1938, and only decades later was it developed as a medical imaging tool. GPS exists because the physicists who built atomic clocks understood the physics of atomic spin with sufficient precision to create oscillators stable enough, and because the engineers who implemented the system corrected for both the relativistic effects of velocity and those of gravity in the satellite orbits. Without correcting for special relativity and general relativity, GPS would accumulate position errors of several kilometers per day. The most abstract physics, the most removed from everyday experience, produced the technologies most present in contemporary daily life. We have reached the end of this journey, but not the end of the subject. The subject has no end. That may be the most important thought to carry from tonight, not as a source of anxiety, but as something closer to relief. The universe is larger than any mind can fully encompass, and that is not a limitation of any particular person. It is the condition of everyone who has ever lived, including the physicists who developed the equations we have described, who spent decades working with a theory that produces perfectly precise predictions and yet still cannot agree on what it means. There is something in the 10 facts of tonight that deserves a moment of attention before sleep arrives, if it has not already. They all share a rupture with what the senses suggest. The senses say that things are in definite places before anyone looks at them. Superposition says no. The senses say that observation is passive, that it merely records what is there. The observer effect says no. The senses say that distant things are independent, that what happens here has no immediate relation to what happens there. Entanglement says no. The senses say that emptiness is empty, that where there is nothing, there is nothing. The quantum vacuum says no, in every case. The reality described by the equations is richer, more connected, stranger, and more powerful than the world that biology equipped us to perceive directly. This does not mean the senses are wrong. It means they were calibrated by evolution to navigate the world at a scale where classical laws are such an accurate approximation of quantum laws that the difference is imperceptible. An organism that processed superposition directly would have difficulty locating food and predators. One that needed to calculate entanglement before every action would not survive long enough to reproduce. Evolution optimized perception for the world it was necessary to navigate, and physics revealed the world that lies beneath that one deeper than any sense can reach. And that deeper world is the same world that is here now, while you rest. The electrons in the atoms of your body are not in fixed orbits like planets around the sun. That image was useful for a few years in the early 20th century, and was then replaced by something more accurate. Electrons exist in orbitals, probability distributions around nuclei, clouds of possibility that describe where the electron could be found if measured, but that do not locate the electron at any specific point while no measurement is being made. These distributions have specific shapes, spheres and dumbbells and more complex forms, determined by the solutions of the Schrödinger equation for the electric potential of the nucleus, and the chemical bonds that hold molecules together are the result of overlaps of these distributions, regions where the wave functions of electrons from different atoms overlap in ways that create states of lower energy than the separated atoms. The stability of solid matter depends on the Pauli exclusion principle, a quantum law that says two fermions, particles with half-integer spin such as electrons and protons, cannot occupy the same quantum state at the same time. It is this law that prevents the electrons of two atoms from completely overlapping when the atoms are compressed. The lowest energy states are already occupied, and additional electrons must go to higher energy states, which increases the total energy and creates a repulsive pressure. Without the Pauli exclusion principle, all matter would collapse. Atoms would have no size, molecules would have no structure, chemistry would not exist, life would be impossible. The solid world you perceive is an emergent effect of a quantum law. Solidity is quantum. There is something paradoxically reassuring in that realization. The universe that created the conditions for you to exist is no less real and no less reliable for obeying laws that intuition cannot fully visualize. The equations that describe superposition and entanglement and tunneling have the same consistency, the same fidelity to observations, the same impossibility of being violated by experiments as the classical laws that describe how a stone falls or how the moon orbits the Earth. There is stability in that consistency. Nature operates according to rules, and the rules work, even when the rules are strange. The physicist Richard Feynman, who contributed fundamentally to the modern formulation of quantum electrodynamics and to the understanding of tunneling, had a way of describing quantum physics that has never been surpassed in honesty. Nobody understands quantum mechanics. It was not pessimism or false modesty. It was a precise observation about what understanding means. We can use the equations, we can predict the results. We can build technologies that work with extraordinary precision from the predictions of the theory. But visualizing what is happening, creating a mental image of an electron in superposition, or two entangled photons in a way that is coherent with what the equations say, without simplifying in ways that betray the theory, that is something no physicist can do completely, because the world the equations describe has no equivalent in any direct human experience. Quantum physics resists visualization for a profound reason. It was discovered in objects no human being has ever seen directly, at scales where no prior human experience prepared the mind for what the equations reveal. That does not prevent us from appreciating what it has revealed. Reality, at its most fundamental level, is more interconnected, more dynamic, more probabilistic, and more responsive to interaction than any everyday image suggests. The boundaries between things are less absolute than they appear. The emptiness is less empty than it appears. The separation between distant objects is less complete than it appears. The determinism of the future is less total than it appears. In every case, the underlying reality has more possibility, more openness, more richness than the surface suggests. It is not a worldview that diminishes what exists. It is a vision that makes it more than any direct perception could ever capture. And while you rest, this reality continues. The sentences can grow shorter now. The electrons in your body remain in their quantum orbitals while you rest. The vacuum seethes with virtual particles every fraction of a second in complete silence on timescales so small that no instrument could register them. Somewhere in the universe, entangled particles remain correlated regardless of any distance between them. The Earth's magnetic field passes through the blanket that warms you, through the air you breathe, and runs through everything that exists between you and the core of the planet. You're inside all of this. You always have been. You could never have been outside. Every atom that you are has passed through superposition, through entanglement, through tunneling, through decoherence, countless times before becoming part of what you are now, and every interaction has silently confirmed, without protocol and without record, the same laws that physicists spent a century mapping with a precision that has no parallel in any other area of human knowledge. You do not need to fully understand quantum mechanics to be made of it. The equations that describe it existed before any application they produced, and they will continue existing after any technology they will yet generate. What did not become completely clear tonight can rest until the right moment arrives. What did become clear is already enough to slightly shift the angle from which anything is seen. You are safe. The universe takes care of you. Everything is in order. The universe that produced the conditions for your existence continues functioning with a consistency that has not failed a single time in the entire observable history of the cosmos. May sleep come gently. The universe continues its silent dance, and we rest in its embrace. Thank you for walking with me tonight. Sleep well.